Hello everyone and welcome back. In today's video, we are going to talk about network analysis in the context of graph theory. However, I'd like to point out that graph theory is in and of itself a whole field of study, so today we are essentially only scratching the surface and discussing the most important aspects of network analysis. Let's start by looking at the Königsberg bridge problem, which is an old mathematical problem based in the old Prussian city of Königsberg. You can see the city map on the left, over here. This problem played a key role in development of topology and graph theory. In the early 18th century, the residents of Königsberg would walk among the city's 7 bridges, the green ones in the picture I just showed you, which were spanning the Pregel River. This river connected 2 central islands, which were themselves connected by a bridge. These are the islands, and this is the bridge that is connecting them. One island was connected to the lower river bank by 2 bridges, A and B. So as you can see over here, A and B, this lowercase a and b. And to the upper bank by 2 bridges, lowercase c and lowercase d. While the other island, or it is more of a peninsula here in this picture, this capital D, I'll call it still an island, that was linked to the south bank by 1 bridge F, and to the north or upper bank by 1 bridge G, as you can see over here. The challenge was to find a walk that would cross each bridge exactly once. So, starting at some land area in one of the 4 areas, capital A, capital B, capital D, or capital C, is it possible to return to our starting location after walking across each of the 7 bridges exactly once? In 1733, Swiss mathematician Leonhard Euler analyzed the problem and proved that such a walk was impossible. How did he reason? So he reasoned that if an island is encountered during the walk, other than at the start or the end, it must have an even number of bridges connected to it, so that each entry to the island could be matched with a departure from the island. In Königsberg, however, island A is connected by 5 bridges, which you can see over here, and landmasses B, C, and D are each connected by 3 bridges. C, B, and D, each connected by 3 bridges. And all of these numbers are odd. This means that the desired walk was impossible. Nearly 150 years later, mathematicians began to represent the Königsberg bridge problem as a graph with nodes or vertices where the vertices represent the land massage. So A, B, C, D are the land masses, and the edges represent the bridges, as you can see. These lowercase a, lowercase c, lowercase b, lowercase d, lowercase e, f, and g. In modern graph theory, a Eulerian path is one that travels through each edge of the graph exactly once. So Euler's conclusion, which states that such a path can exist only if a graph has at most 2 vertices of an odd degree, becomes the first theorem in graph theory. And now let's look at some use cases of graph theory. So, first of all, social networks revolve around connections, and platforms like Facebook, Instagram, and LinkedIn have grown largely due to graph analytics. Graph analytics play a key role in identifying influencers and communities within social media networks. Influencer marketing on social media is becoming more popular as the number of users grows and as customers become more skeptical of traditional marketing methods. Then, medical and life science research often focuses on connections and dependencies. Analyzing massive datasets can make it challenging for scientists to uncover the insights needed to drive the research forward. Graph analytics offers numerous applications in medical research. It can be used to identify links between drugs and their adverse effects and to track the spread of diseases, including aggressively spreading viruses like we had COVID-19, for instance. Also, a lot of research has addressed patient networks in healthcare. Sorry for this. Analyzing patient data to identify treatment patterns and outcomes is another big use case in healthcare. Graph analytics optimizes also supply chains and logistic operations by modeling and analyzing networks of suppliers, manufacturers, distributors, and so on. Some use cases here would be route optimization, so finding the most efficient path for transportation and delivery, supplier networks by analyzing relationships between suppliers to identify potential risks and optimize sourcing, for instance. And another use case here would be inventory management. So here we can track the flow of goods through supply chains to improve inventory management. And last but not least, in telecommunications, graph analytics helps in understanding network structures, optimizing operations, and improving customer experience. Some use cases here, network optimization, for instance, analyzing the structure of communication networks to optimize performance and reduce costs. And we can have also fraud detection, in which we can detect fraudulent activities, analyzing call details, records, for instance. But let's recall some formal definitions about graphs first. A simple graph G consists of two sets, a finite non-empty set of vertices, V, and a finite possibly empty set of edges, E. Vertices are also called nodes, and edges are also called links or arcs. In many applications, the edges of a graph are assigned weights. These weights may represent the distance from one vertex to another, or the cost of going from one vertex to an adjacent vertex. A graph with weighted edges is called a network. A subgraph of G is a graph G prime such that the set of vertices of G prime is included in the set of vertices of G, and the set of edges of G prime is included in the set of edges of G. And now if we look at multigraphs, what is a multigraph? A multigraph G consists of a set V of vertices, a set E of edges, and a function f from E to this set of pairs U and V, where U and V are part of the set of vertices and they're different. And edges E1 and E2 are called multiple or parallel if f of E1 is equal to f of E2. An example of multigraph you can find here in the second figure over here, where we have vertices U, V, and W, and then we have these two parallel edges between U and V, E1 and E2. Now, let's remind us what is an undirected graph. An undirected graph is one in which the pair of vertices representing any edge is unordered or bidirectional. So that means that the edge from U to V is the same as the edge from V to U. And an example of an undirected graph is in the upmost figure here on the right side. This is an undirected graph. A directed graph, on the other hand, or it is also called a digraph, is one in which we represent each edge as a directed pair of vertices, U and V, as you can see over here, in which U is the tail and V is called the head. But probably you knew all of this. However, let's briefly recap the graphs we looked into earlier, and we have a classification in this table based on the edges types, whether multiple edges are allowed or not, or whether loops are allowed or not. Oh, and I forgot to mention that there are no loops in a simple graph. So in a simple graph, we have undirected edges, no multiple edges are allowed, and no loops are allowed. In a multigraph, we have undirected edges, multiple edges are allowed, but there are no loops. In a directed graph, we have, of course, directed edges, no multiple edges are allowed, and loops are allowed. And in a directed multigraph, we have directed edges, and both multiple edges and loops are allowed. But now let's take a look at some examples of networks. We will define them based on vertices and edges, and keep in mind that both vertices and edges can have attributes. For instance, in an airlines network, we could have as vertices the airports, and as edges the routes or the planes themselves, and we can have some attributes. Like I said, associated with both vertices and edges. So for airports, we could have as attributes terminals, the number of people working the airport, the population of city that the airport is located in, whether it operates on international or domestic routes, the hangar capacity, and the list can go on. Then, if you look at the edges, we can also have attributes for them, such as passenger number, if we talk about the planes, and plane type, fuel usage, distance covered, whether there are empty seats on the plane, etc. We could have then banking networks where we could consider account holders as vertices and transactions as edges. And as attributes for vertices, for instance, we could have as attributes the name of the account holder, the demographics the holder is part of, the banking products that the account holder takes into use, their account status, the balance, and so many other details that could be included here that concern the account holder themselves. Then, if we look at attributes for the transactions over here, we could have the type of the transaction, the authentication type, the time and location, the device used, and so on. Maybe the most common network, or let's say the most intuitive one that we deal with on a daily basis is the social networks, where the vertices are us, the users, and then the attributes are our names or nicknames, if you will, the demographic we are part of. For instance, age, gender, our connections, our likes, comments, subscriptions, the groups we are part of, and so on. And here the edges are based on our interactions. So how do we interact with each other? We have different types of interactions. For instance, likes, comments, DMs, what is the time of the interaction, the duration, the type of the content we are following, the topics of the content, and so on. Another type of network is, for instance, the medical network, where we consider the physicians as vertices and the patients as links or edges between them. So in a way, the intuition here is that doctors can share patient information with each other. So every time we visit the doctor, the physician has access to previous information and can have a comprehensive view of the medical history of the patient. And attributes for the physician here, we could have the specialty, the experience, the affiliation, the weekly patient intake, and so on. And if we consider the edges as the patients, then we can have the demographic of the patient, the diagnosis, how frequent they visit the doctor, if they have any referrals for specialists, what is their insurance type, and so on. And last but not least, the supply chain networks. These are quite classical networks because there are classical problems that are associated with them and different optimization techniques here. So for instance, we could have warehouses as vertices, and as attributes, we can have the location, the size, the capacity, the storage type, connectivity, where the warehouse is automated or not, And for edges, we can have trucks, for instance, but also ships or planes. Then as attributes based on which type of transportation vehicles we have available, it could be the load capacity, the year of make, the geographical permit for the vehicle, the miles traveled, maintenance status, the driver or the captain experience, and so on. And if we go back now to more formal definitions, we have the following. So if we have an undirected graph like the one over here, if UV is an edge in the undirected graph, so as this edge over here, U and V are called adjacent. The edge UV, so this one, is incident on vertices U and V. Then, if UV is an edge in a directed graph like the one over here, U is adjacent to V and V is adjacent from U. And then the edge UV, this one over here, is incident on U and V. So with this in mind, let's look at the adjacency matrix. So let G be a graph with n vertices. The adjacency matrix of G is a matrix that we denote as adjacency matrix, edge mat, if the edge Vi, Vj is in the set of edges Eg, then the entry in the adjacency matrix at position Ij, which is this adjacency matrix Ij, is 1. And if there is no such edge in Eg, then the value there is 0. The adjacency matrix for an undirected graph is symmetric. The adjacency matrix for a digraph or for a directed graph doesn't need to be symmetric. Some advantages of the adjacency matrix is that determining the connections of vertices is easy. The degree of a vertex is calculated with a formula for an undirected graph here. And for a digraph or directed graph, on the other hand, we have an in degree and an out degree formula based on the row sum and on the column sum. And the drawback of an adjacency matrix is that for sparse graphs, most of the terms in the adjacency matrix are equal to 0. So we can take a look at an example of adjacency matrix over here. So if we have this directed graph over here, we have, for instance, a link from vertex A to vertex C, and the weight is 8, and from vertex A to vertex D, A to D, and the weight is 4. But another observations I like to make here, directed multigraphs also can be represented using an adjacency matrix, but instead of having the number 1, where there is an edge from Vi to Vj, we can have the number of edges from Vi to Vj on that position. And adjacency is chosen on the ordering of vertices. So there are as many as n factorial such matrices, where you remember there are n vertices. So this adjacency matrix is not unique. The adjacency matrix of simple graphs are symmetric. So Aij is Aji. Now I would like you to think about why that is. Another observation is that when there are relatively few edges in the graph, the adjacency matrix is a sparse matrix, like I said earlier. And now let's look at another representation. This is an adjacency list. First, let's replace the n rows of the adjacency matrix with n linked lists, one for each vertex in the graph G. So for an undirected graph with n vertices and e edges, we have n head nodes and 2 e list nodes, right? And for a directed graph with n vertices and e edges, we have n head nodes and E-list nodes. So if we look over here for node A, we have C and D as the neighbors, and we have these weights 8 and 4, right? And if we think about the trade-offs now, for a sparse graph where most vertex pairs are not connected by edges, an adjacency list is much more space efficient than an adjacency matrix. The space required for an adjacency list is proportional to the number of edges and vertices in the graph, where the space needed for an adjacency matrix is proportional to the square of the number of vertices. This is another little problem I would like you to think about. And now let's look at the degree of a vertex. The degree of a vertex V in an undirected graph G is denoted by this degree of V and is defined to be the number of edges incident to it. If the degree of V is 0, then we call V isolated. And if the degree of V is 1, then we call it pendant. So if G is a directed graph, then we define the in degree of a vertex as the number of edges for which the vertex is the head, and the out degree of a vertex as the number of edges for which the vertex is the tail. Now, one big theorem in graph theory is this handshaking theorem that you can see over here that reads as follows. So, for an undirected graph G with n vertices and e edges, if di is the degree of vertex I in G, then the number of edges in G is given by this formula. And we're not going to prove this formula, this theorem here, but this is a classical theorem and is definitely worth remembering. So I would like you at least to remember this. And now let's do some more basic definitions because they're important. So a path from a vertex U to a vertex V in a graph G is a sequence of vertices. Sorry for this again. Where no vertex can be repeated. So we have an example here. We have A, B, C, D, E. This is a path. Then a trail, no edge can be repeated. So in a trail, we can have A, B, C, D, E, B, D. So this is a trail. And in a walk, no restrictions are applied. So an example of a walk, we could have A, B, D, A, B, C, sorry. A graph is closed if the starting vertex is also the ending vertex. And the length is the number of edges in the path, in the trail, or in the walk. Now, a circuit is a closed trail. An example of a circuit here, we have A, B, C, D, B, E, D, A, right? So this is a circuit. And then a cycle is just a closed path. So this is the A, B, C, D, and A again. This is very simple to remember. And if we look now at connectedness, an undirected graph is connected if there is a path between every pair of distinct vertices in the graph. So a representation example here. So this graph G over here is connected since for every vertex in the set of vertices V1, V5, there is a possible path between them, right? You can go from V1 to V5, you can go from V5 to V3, to V4, to V2, to V1, and so on. And then in an undirected graph, we could also have another notion of being disconnected. So if it is not connected, we call it disconnected. And we say that we disconnect a graph when we remove either vertices or edges or both to produce this disconnected graph. And now a few more definitions. An articulation point, which is also called a cut vertex, is a vertex whose removal produces a subgraph with more connected components than in the original graph. And the removal of a cut vertex from a connected graph produces a graph that is not connected. A cut edge is an edge whose removal produces a subgraph with more connected components than in the original graph. So if we have in this representation example, in this graph G over here, V3, this red one, is the articulation point. And for instance, edge V2, V3 is a cut edge because the number of connected components is 2 in both cases, which is more than 1 if we take the graph by itself, right? Now, if we look at directed graphs, a directed graph is strongly connected if every vertex is reachable from every vertex. So for any two vertices A and B in the graph, there is a path from A to B and from B to A. And a directed graph is weakly connected if a path exists between every two vertices in the underlying undirected path. So, in other words, a directed graph is weakly connected if replacing all of its directed edges with undirected edges produces a connected undirected graph. So for representation, we look here, G1 is a strong component, right? Because every vertex is reachable from every vertex. And then this is weakly connected because there isn't always a path. And this is G3, the undirected representation of it, right? And if we look at strongly connected components, these are subgraphs of a graph that are strongly connected. So G1 over here is a strongly connected component in G, and you can see why. And now that we looked at all these definitions and we reminded them, let's look at centrality. Centrality is a key concept in graph analytics and focuses on identifying significant nodes within a graph. It highlights nodes that stand out in terms of importance or centrality compared to other nodes. There are different metrics here that are used to assess each node's importance from different angles, providing detailed insights into the graph overall. And these metrics can offer different perspectives on node analysis. And they're helping us to extract information from a network in an effective way, because otherwise, if you have a huge network, it can become very cumbersome and very overwhelming. You don't know where to end, you don't know where to start, which nodes are important, which are not, and so on. So understanding these measures is really crucial for choosing the most suitable ones, for instance, for visualization. So first of all is degree centrality, which defines the importance of a node based on the degree of that node. And the higher the degree, the more crucial it becomes in the graph. So this is used to find popular individuals, the most connected individuals, those who connect quickly, more quickly in a wide network, or the ones that hold more information. And it's one of the simplest centrality measures of node connectivity. And something that you need to remember here is that for directed nets, you have two separate measures actually, an in degree and an out degree, like we saw earlier on as well. Then we have closeness centrality. And for closeness centrality, here we identify a node's importance based on how close it is to all the other nodes in the graph. And we define this closest as the number of links included in the shortest path between two nodes. So to calculate the closeness of a node, we sum up all these distances from that node to all the other nodes in the network of the graph. The closeness centrality finds application in identifying, for instance, individuals that are in a position to influence the entire network in a fast way, maybe in the fastest way possible. It's also used to identify influences outside a highly connected network. So individuals with a high score of this centrality can acquire and control crucial information within the network. And maybe a third application would be to predict the importance of words in a particular document on the basis of graph-based key phrase extraction process, for instance. There are other types of centrality. For instance, there is a harmonic centrality, which is a type of closeness centrality. This gives a measure which is more accurate in the case where some of the nodes are outside of the perimeter of reach. And then finally, we have the betweenness centrality, which defines the importance of any node based on the number of times it occurs in the shortest path between other nodes. So it measures essentially the percent of the shortest path in a network where a particular node lies in that path. A node with high betweenness centrality is considered the most influential over the other nodes in the network. So betweenness centrality is used, for instance, to measure the network for telecommunication networks or e-commerce package delivery processes. In addition, so microbloggers, so bloggers that don't have so much reach, use this centrality to enhance their reach. For instance, on Twitter, with the assistance of a recommendation engine. And it shows who they should connect to form a bigger communication network. And then there are other types of centrality measures like eigenvector centrality, then there is page rank centrality, and then there is article rank and so on, but we're not going to cover all of them here. They're quite specific. And the last thing I would like us to look at is network density. This is also very important. This is the ratio of the number of actual links to the possible or potential links of a network. And it's based on these two numbers that you can see in this formula. So this is the number of vertices, the cardinality of the V set, and this is the number of edges, so the cardinality of the E set. So network density is a measure that represents the proportion of actual connections relative to the total possible connections within a network. So it is crucial in network analysis because it provides insights into the overall connectivity of the network. So a network's density is calculated as this ratio of existing edges, so actual connections, over the maximum possible edges, so potential connections, and it has values based on this ranging between 0 and 1. A value which is closer to 1 indicates a highly interconnected network, and the value of 0 indicates a sparse network with few connections. And then a high density network also characterizes networks where nodes are highly interconnected, like I said, but that means that they're often very robust with multiple pathways for information flow But what they risk here is the redundancy and information overload. And in low density networks, these are, like I said, the ones with fewer connections. Here, we have potentially communication challenges because there aren't so many connections. And they can also foster innovation by connecting diverse, otherwise unlinked clusters, for instance, sometimes. But to reach optimal density, we talk about a network that balances efficient communication and resources, for instance, resource sharing actually, without overwhelming the network or having excessive redundancy, right? So if we look for undirected graphs, we have this, the number of possible links would be this, and then this is mu. Is basically n, if n is the number of vertices, n multiplied by n minus 1 over 2. I'm going to let you think about why that is. And then the network density is the number of edges over the number of all the possible links, which is this number. So this comes here, and then we have this kind of formula. And then for directed graphs, the number of possible links is n multiplied by n minus 1. I'm going to also let you think about why that is. Then here the network density is the number of edges over the total number, possible number of links. So with all this in mind, I'd like to thank you for watching and then see you in the next video.